So, if you saw my thumbnail, you know I'm claiming this is a map. But to me, it looks more like a butterfly than it does a map. That's because this isn't a map of a place. It's a map of concepts with different regions dedicated to topics like space, cars, and sails. To understand what each dot means, we're going to need to enter the world of natural language processing, NLP. That is, writing computer programs to understand human text and documents. To understand natural language processing, we should get a data set of some natural language text to process. For this, I'm going to turn to a data set of Usenet posts. Usenet was essentially the world's first social media, but invented in 1980, when computers looked a bit more like this. So everything was based on text exchanges. Usenet was arranged around various thematic topic groups. Here I pulled some topics from the comp.graphics newsgroup, which hosted discussions on computer graphics. We can see an example document here discussing Pixar's 3D rendering software called RenderMan, another one discussing C++ graphics libraries, and a third on creating 3D stereo images. Comp.graphics was just one of many different computer-themed newsgroups, and Usenet had other newsgroups centered around other various topics like news, science, music, and many other areas. So, what does our Usenet text dataset look like? We'll have a collection of messages from a variety of different news groups. Here's an example message from the For Sale news group. Hi, I have several computer-related books for sale. They're all unused and hence in excellent condition. They're all unused. Oh no, read your programming books. Okay, or maybe just watch my YouTube videos. Okay, another example. We can go to the Space news group, and here we find an example of, can anyone tell me where I might find stereo images of planetary and planetary satellite surfaces? GIFs preferred. I can tell they pronounced a GIF from how they spelled it. Okay, from the politics group, we have Clinton has backed off the $16 billion jobs bill. This is President Bill Clinton. Can you tell that Usenet peaked in popularity in the early 90s? And finally, we can take an example from the Cars news group. I brought an Intrepid about 2 months ago, and I'm very happy with it. For clarity, let's simplify each one of these documents into a single representative sentence. I have several used books for sale. I brought a used car and I'm happy with that car. Where can I find the planetary images? And the president backed off from the bill. Now our goal is to turn these text documents written in a natural language into vectors, that is a list of numbers which somehow represent the document mathematically, numerically. We can first do some pre-processing to simplify the text further. Step 1 is to remove any punctuation, and step 2 is to make any uppercase letters lowercase to simplify things a bit. These processed documents still have a lot of words that are unlikely to be informative, like I, for, and, the, and so on. We can often remove these uninformative words, sometimes called stop words, without losing too much from the sentences. In this case, we're left with several used books sale, brought used car happy car, find planetary image, and president backed bill. I think you can still tell what was going on in the original documents from these simplified, streamlined sentences. But if you remember, our goal was to turn each one of these documents into a mathematical numerical vector. The first step here is to make a dictionary of all the words seen across all the documents. Backed, bill, books, brought, car, and so on. We can now count how often each word appears in each document. Our first sentence, several used books sale, has one of each word, books, sale, several, and used. 1, 1, 1, 1. Our second sentence has one brought, one happy, one used, and 2 car. 1, 2, 1, 1. Document 3 has find, images, and planetary. And document 4 has bill, backed, and president. We can fill in the zeros to complete our counts. Now we have our vectors, which are simply the counts of each word in that document. So for the first document, the vector becomes 001, 000, 001, 1001. And each other document can similarly become a vector of counts, leading to one vector for each document. Here, each word had equal weight, but it's also popular to give rare words like president and images more weight than words seen in many documents like used. So we have vectors. Now let's try to visualize them. The challenge is, if we have thousands of documents, each hundreds of words long, looking at a list of vectors isn't going to be very informative. It's just a big list of numbers. What can we do? Here we can turn to PCA, Principal Component Analysis, which is honestly one of my all-time favorite algorithms. We don't have time here to go into how PCA works, but what it does is shrink a group of large vectors into a group of smaller vectors, which still captures the essential statistical relationship between the vectors while shrinking their size. We call the length of a vector its dimension, so PCA is a dimensionality reduction algorithm. For example, we can use PCA to reduce the high-dimensional document word count vectors into, say, three-dimensional vectors. Why 3D? Well, I can plot the 3D points of each document, giving us a visualization of the document space. So what I've done is taken hundreds of documents from 4 different news groups on the topics of space, politics, cars, and for sale, for a total of a little over 2,000 Usenet postings. For each document in our dataset, we turned them into a weighted word count vector, which was then reduced to 3 dimensions using PCA. And here's the result. Let me animate the camera and, oh, you can clearly see some 3D structure. There appears to be 3 or 4 wings or clusters of postings jutting out from the center. Perhaps each of these wings corresponds to some trend in the documents? Well, to see the structure better, let's color each dot based on which news group it came from. We have green for space, red for politics, and so on. Now we can see that each wing or branch of clusters roughly corresponds to one of the 4 topics. Even though PCA didn't have access to which news group each posting came from, it was still able to group documents together based on the underlying topics in the documents. This ability to recover structure in the data without knowing the true labels is called unsupervised learning, and it's a vital foundation of the modern big data and AI revolution. To dig in a little deeper, let's look at a flat 2D PCA space. You can see we've recovered our butterfly from the start of the video, though now with colorful wings to help visualize the structure. The first principal component on the x-axis captures a spectrum from money to politics. The second principal component on the y-axis captures more about space versus cars. And we can see that the 4 wings of our butterfly come from the 4 clusters in our dataset, roughly 1 for each news group topic. Looking a bit closer, you can see the clustering doesn't perfectly match the Usenet news groups the documents came from. For example, we have some red for sale dots here in the middle of a blue cars region. What's going on here? Well, we can read one of the documents to see. For sale, 1964 Ford Galaxy 500, 4 doors, light blue, 56,000 miles. Yes, that's correct. It was her second car. So this was in the for sale news group, but PCA understands that it's about cars, so it gets clustered with other car documents. Here's another example. It's a case where a green space document is found in the middle of an orange politics area of the PCA space. How did this happen? Well, let's look at the document. The document from the space group reads, "It's called a democracy. Majority rules. Sorry if you don't like it. I suggest you modify the Constitution to include a constitutional right to dark skies." Wow, I'm going to agree with PCA here. Sounds like politics to me. So to recap, text can be turned into vectors based off of word counts and word frequencies. PCA, or other dimensionality reduction techniques, can then be used to turn this high-dimensional data into low-dimensional visualizations. And finally, unsupervised learning that happens through dimensionality reduction can reveal structure in the data without needing to know any labels from the data. So, what's next? You can use these techniques to try to classify text based on training data, for example, to automatically tell if a message is spam or not based off of what regions of PCA space it lies in. As I mentioned earlier, we can improve our results by weighing rare words more than common ones. For the results here, I've done that. I've used a technique called TF-IDF, which gives more importance to words that appear in fewer documents. And finally, using custom neural networks can give the best results. A special network structure called the transformer was invented for use with text data, and it's what drives generative AI like ChatGPT. More on that in a future video. Thanks for watching. I'll see you next time.